Hello, everybody. Welcome to lecture on chapter number 9. So, chapter number 9 is on designing database. And when I was designing this course, uh, I was first I was inclined not to include this chapter in our coursework. Uh, because I'm assuming everybody who's taking MBA 535, you are doing MIS specialization. So either you have taken my MBA 545 or you will take my MBA 545. So in that course, we spend roughly 6 weeks, 5, 6 weeks on designing databases and ER diagram. So basically chapter number 7 and this chapter number 9, I do this roughly 5, 6 weeks of that in my MBA 545 and very hands-on. We do ER diagrams, SQL, and all those things. And I think nearly half of this class have taken my MBA 45, and I know there are a lot of undergraduate students who are taking this class, and they have taken my MIS 470, where I spent 16 weeks on this database. So I was first inclined not to include this chapter, but then I thought, just for the having a completeness to this course, I will include it. So this chapter talks about designing databases, but as I said, if you have not taken my MBA 545, there we will go quite hands-on on designing database, and I'll teach SQL as well. Okay. So we have so you have your entity relationship diagram done. Entity relationship diagram with your entities, relationships among entities, attributes, defined identifiers, which are like your primary keys. So you are ready with those, and now the time has come to convert those ER diagrams into a physical table, a database. And before we do that, we have another step in between where we convert our ER diagram into relational data model. A lot of times from ER diagram, you can skip this step because at ER diagram stage, we have taken care of all the things which are required under relational data model, which I'll show you in a minute. So a lot of time, if you take care of all the issues which you fix in relational data model, so you address these at ER diagram stage, you can skip this. Another place where this doing relational data model via normalization makes a lot of sense is when you are updating an existing database, which let's say was created 5-10 years back, and you want to improve it, fix it. You want to improve its ER diagram, or you don't even have access to its ER diagram, so there's an existing database and you want to upgrade it, fix it, and for that normalization is a very good process. Or let's say you have an Excel based system or some other application based system, a flat file based system, and then you want to convert that into a database. So there again, relational data model is very helpful there. So let's learn what is. So how does ER diagram connects to relational model? So what we call entity is called a relational model, which then becomes a table. Attribute is again called attribute, and in database it's a column. Identifier is called a key, a primary key, foreign key, and in database also it's called primary key and foreign key. So those are some of the sort of terminology. So what is this relation? Okay, so relation is, we are adding one more layer on top of our ER diagram to make sure that we have the best structured and logical database design. And what relation is in that sense is it's a two-dimensional table of data which consists of rows and records. Of course, pretty straightforward. But there are certain criteria which you have to fulfill in a relation. That is, the table must have a unique name. Every attribute must be atomic. Like for example, you cannot have attributes like addresses or skill anymore. So address needs to be broken down into address, city, state, zip code, country, and skill would be have its own entity, so that you can enter multiple skills. So that's what it means by attribute must be atomic. So a single value goes in every attribute under entity. At the ER diagram stage, you can have attributes like name or address, but under when you do relational model, you break them into first name, last name, and for address, as I said, address, city, zip code, and things like that. And as I was mentioning earlier, that if you take care of all these things at your ER diagram, which we did. So when I teach ER diagrams, I ask students to, instead of using name, start having attributes as first name and last name, and break address into address or street address, city, zip code. So we have already taken taken care of these things. Every row must be unique in a relation. That means if I am entering 2 rows of data, student A and student B, they should be unique. So by saying they should be unique, it doesn't mean that every field name should be unique. But if I look at, let's say this is a table, so if I look at these 2 records, let me grab something here. Okay, I was just trying to find something to draw or point. It looks like it's not available in my version, so that's fine. So coming back to it, every row must be unique. So what I mean by that, how do we achieve that, is that doesn't mean that, let's say for employee ID 100, all the column names should be unique. No, in totality, they should be unique. So let's say 2 employees have same name, they're in same department, same salary. But their employee ID would be different. So in totality, if you look at the whole record, even if 2 people have the same name, same department, same salary, but their employee ID would always be different, and that's how each row is unique. Column names in tables must be unique. So all these column names must be unique, which we are doing in the ER diagram as well. The order of the columns and the order of the rows are irrelevant. So what that means is you have created ER diagrams, now creating tables. So whether I write department first or name first or second, that does not make a difference. If I enter Margaret records first and Chris record third, or other way around, that also doesn't make any difference. So the order of the column in a table has no meaning. It does not have any effect on when we are creating a report, and so does the data entry. Whichever sequence we go in, maybe I enter Susan record first, then Chris, then Margaret, that also has no effect when we are pulling the data out. So these are some of the things a relation should satisfy. And when we were talking about every row must be unique, how do we make sure every row is unique? By having something like employee ID, student ID, social security number, driving license ID, product ID, customer ID, patient ID. All these are examples of primary key. So primary key is a unique identifier or a column name like employee ID, which is unique for every row of data. And its property is that it's always not null, not empty, and it's unique. So again, we need some way to have each row of data unique. 2 people can have same name, same department, but they cannot have same primary key, which in this case is employee ID. In your case, in university database, is student ID and things like that. And in ER diagram stage also, you had you mark something as identifier key or as primary key. So we have done that in ER diagram as well. Foreign key I'll skip for now. I think it's a little bit more complex concept. You need to have a little bit more understanding of tables or database. So if you have taken my MBA 545, which we covered it there. If not, wait for that class and I'll go over this a little bit more in there, because there we are doing all the hands-on work, so it's a little bit more easy to understand. Okay, so now this is what are all the requirements of the table. And why are we doing all these requirements? So that we can avoid these three anomalies: insertion anomaly, deletion anomaly, modification anomaly. Now, what are these anomalies? So if you look at this table, which somebody designed without ER diagram or doing a relational model, they didn't do any of those things. And as you can see, this table has all these three: insertion anomaly, deletion anomaly, modification anomaly. So what does that mean? So let's look at an insertion. I cannot enter a new employee without having the employee taking a class. So if a new employee joins it, I will say 151 Nitin Walia, education, XYZ salary, course title, system analysis. Oh, sorry. This is a course what that employee has taken. So when a new employee comes, he or she has not taken any course. So I'm forced to enter some record for that or keep it blank. So this is an example of where you have insertion anomaly. We're adding sort of a new record. I need to enter some record for course title, or you will have sort of duplicate data there. Okay. The second one is deletion anomaly. Deleting rows may cause a loss of data that would be needed for future use. So for example, if let's say Ellen decides to leave our company, and Ellen is the only one who has taken a tax accounting course. He leaves our company and I delete his record. With his record, the tax accounting information will go as well. So if tomorrow somebody comes to us and say, hey, what kind of courses we are available? Can you give me their title name? And if Ellen's record is gone, the tax accounting goes with it as well. We will not know through our database that that course is available as well. Third is modification anomaly. That is changing data in a single row forces changes to other rows as well. Margaret, let's say, got a promotion and her salary increased from $48,000 to $58,000. So I have to come and make change in this table, in this row of data, and in this row of data as well. So this was a simple example to show you that how the way we are storing data in this table violates all these three conditions: insertion anomaly, deletion anomaly, and modification anomaly. So that means this relation or this table, let's call this whatever this is, this does not fulfill the criteria of a relation. And if it does not fulfill the criteria of relation, it cannot be converted into, or should not be converted into, a relational database. So now this table has all these three anomalies. It's not a relation, still not a relational data model. So how do we fix it? You fix it by doing something called data normalization. And I was saying earlier, it's a process of converting existing relations which have anomalies in them, like this. So it has some anomalies which we need to fix so that it fulfills all the criteria of a relation which we mentioned here, and only then we can convert it into a physical database, a table. And another good place where we use normalization is, as I mentioned, you have a very old database, you don't know what ER diagram you used for that, or somebody else used it and that person is gone, or you have an Excel based system. Actually, this looks like a perfect example of how somebody might be storing data in Excel. So you want to convert that Excel way of storing data, you see their requirements, and now you want to convert that into a relation and then a database. And that's what normalization is, the process of converting data structures into well-structured relations. And how do we do that? We follow 3 steps. It's not, looks like it's missing. Let me go here. How do we do that? We do that by following a process called normalization, where you convert your existing relation or existing data file first into first normal form, first NF, second NF, and third NF. You do have the possibility to go up to 5 NF, but we do not need to. After you have reached the third NF stage, you fulfill all the requirements of a relational database, and generally that's where we will stop, at the 3 NF. So again, so you will have something like this, an existing problematic relation, and we will apply 1 NF, 2 NF, 3 NF to convert into a relation, and then store it into, to convert it into a database. So how do we do that? Before we do that, some definitions or some background or understanding of what is functional dependency.